Before we begin to learn about atomic spectra, let's understand the term spectrum. When a ray of white light from the sun or an incandescent lamp is passed through a prism, it is dispersed into a continuous array of 7 colors, namely vibgyor. This is called spectrum. It is observed that in a spectrum, the radiation with lower wavelength bends more than the radiation with higher wavelength. That is why we see violet with lower wavelength at 400 nanometers and red with higher wavelength at 700 nanometers in the spectrum. The most common example of a spectrum visible to naked eye is a rainbow, consisting of 7 colors that constitute the white light. These colored bands merge into each other. Therefore, the spectrum of ordinary white light is called continuous spectrum. Electromagnetic radiations include a range of wavelengths, and this array of wavelengths is referred as the electromagnetic spectrum. When electromagnetic radiation interacts with matter, atoms and molecules, they absorb some part of radiation and go to a higher, unstable energy state called excited state. As the atoms are unstable in their excited states, they tend to revert to its original state, called the ground state, by emitting the same amount of energy that it had absorbed earlier. This energy can be emitted in a single step or in a number of steps. Depending on the amount of energy emitted, a radiation of particular wavelength is obtained. The spectrum of radiation emitted by an atom is called emission spectrum. In contrast to the continuous spectrum of white light, an emission spectrum is usually discontinuous with dark spaces between the bright lines. Such a spectrum is called line spectrum. The bright lines in the emission spectrum exist due to the fact that emitted radiations are only of specific wavelengths rather than a continuous spread of wavelengths as in the case of white light. A photographic negative of emission spectrum is the absorption spectrum. An absorption spectrum is recorded by passing a continuum of radiation through a sample which absorbs radiation of certain wavelengths. The missing wavelengths that correspond to the radiation absorbed by the matter leave dark spaces in the bright continuous spectrum. Unlike emission spectrum, absorption spectrum consists of a series of dark lines in the bright continuous spectrum. The study of emission or absorption spectra to determine the molecular structure is referred as spectroscopy. The emission spectra is also called atomic spectra, sometimes because each atom has a unique emission spectrum, just like each human being has unique fingerprints. The characteristic lines in atomic spectra can therefore be used in chemical analysis to identify unknown atoms. German chemist Robert Bunsen was one of the first investigators who used atomic spectra to identify elements. Elements like rubidium, cesium, thallium, indium, gallium, and scandium were discovered when their minerals were analyzed by the spectroscopic method. The presence of helium was also detected in the Sun by means of the spectroscopic method. Now, let us study the line spectrum of hydrogen, which is a one-electron system. When an electric discharge is passed through hydrogen gas, hydrogen molecules dissociate to produce energetically excited hydrogen atoms. These excited atoms emit electromagnetic radiation of discrete frequencies, while coming back to lower energy levels. The resultant hydrogen spectrum consists of multiple series of lines that are named after their discoverers. The first series in the hydrogen atomic spectrum, Balmer series, was discovered by Johann Jacob Balmer in 1885. Its lines belong to the visible spectrum of electromagnetic radiation. These are observed when the electrons jump from n greater than or equal to 3 to n equal to 2 principal energy level. Balmer showed that if spectral lines are expressed in terms of wave number, then the visible lines of the hydrogen spectrum obey the formula wave number, nu bar equal to 1,09,677 multiplied by 1 divided by 2 square minus 1 divided by n square per centimeter. Here, n is an integer equal to 3, 4, 5, etc. Balmer's formula inspired the Swedish spectroscopist Johannes Rydberg to come up with a modified formula to describe all series of lines in the hydrogen spectrum. The equation may be written as wave number nu bar is equal to 1,09,677 multiplied by 1 divided by n1 square minus 1 divided by n2 square per centimeter. Here, n1 is equal to 1, 2, 3, etc. and n2 is equal to n1 plus 1, n1 plus 2, etc. The value 1,09,677 per centimeter is called the Rydberg constant for hydrogen. The first 5 series of lines that correspond to n1 equal to 1, 2, 3, 4, and 5 are known as Lyman, Balmer, Bastian, Brackett, and Fund series respectively. Each of these series, shown in the table, represents the line spectrum emitted by the electrons of hydrogen atom when they change state from N2 to N1 principal energy levels. Here, N1 and N2 represents the lower and higher energy levels respectively.